Hello, everyone. We are going to continue sequences, and this is part two. So far we learned about like sequences are built or how to find limits of sequences. Now we are going to talk a little bit of like more investigating into sequences. And if it's not very easy to find limit mathematically, do we have any other tools? So we are going to start with definition. And my definition is going to be a definition of increasing or decreasing sequence. So definition. The sequence AN is increasing if every next element of that sequence is greater than the previous. So previous element is less than the next one. So for all n greater or equal than 1. Also sequence which is increasing called monotonic. Example of increasing sequence is just a sequence of natural numbers 1, 2, 3, 4, and so on. We see that every next element is greater than the previous. 4 is greater than 3, and greater than 2 and greater than 1, and this sequence is continuing infinitely with the same relation between terms. Let's say that was the first part of our definition. The second part of our definition is going to talk about decreasing sequence. AN is decreasing if the inequality is opposite direction. Next element is less than previous element. So previous element AN is going to be greater than the next element. Also for all n greater or equal than 1. Such sequence is also called monotonic. So monotonic is either increasing or decreasing, but to be more specific, you can say increasing or decreasing. If you don't want to be specific, you can just say monotonic. I'm going to give you an example of such a decreasing sequence. Sequence is 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. We can see that 1 over 2 is greater than 1 over 3, is greater than 1 over 4, is greater than 1 over 5, and it's going to be repeated forever. So the typical example of decreasing sequence. Here it's easy to see that the sequence is increasing or decreasing just by kind of using like our common sense maybe. The idea is that natural numbers are increasing, but not all sequences are going to be that easy to define whether they are decreasing and increasing. And not all sequences are going to be decreasing or increasing. There are some sequences which are not monotonic. I'm going to give you an example. Non-monotonic. Example of non-monotonic sequence is going to look like this. 1 minus 1, 1 minus 1, and so on. So this sequence decreases and then increases, decreases, increases, decreases, increases, non-monotonic. It's not doing some one thing like increasing or decreasing. Non-monotonic sequences exist in nature and there are lots of them, so don't worry that all sequences are monotonic. Okay, so let's talk about the ways to verify the sequence is monotonic or non-monotonic. I'm going to consider a simple sequence and show you two ways to verify whether the sequence is increasing or decreasing. So my example is going to look like this. I'm going to consider sequence AN equals 3 over n plus 5. Well, it's kind of basically very similar to this sequence of 1 over 2, just kind of slightly different numerator and slightly different denominator. But we are not going to rely here on just common sense. We are going to rely on math. We are going to prove that the sequence is decreasing. So I'm going to kind of ask a question. Is it decreasing? How can we kind of show that the sequence is decreasing if it's not obvious? There are two ways to do this. Way one, we just literally can prove the inequality of decreasing sequence, that element an is greater than element an plus 1 in general. What I'll need to do to prove this? Well, I'll need to place element an over here, 3 over n plus 5. And I'm going to prove, I'll show that element n plus 1, where n is 1 unit greater, this is n plus 1, is going to be less. So basically, guys, it's not known yet. I'm going to check if it's true or not true. So I'm trying to check if the inequality is true. So what I'm going to do with this inequality? Well, because both my denominators are positive, I'm going to multiply, kind of crisscross my kind of expression by it. So I'm going to multiply, I'm going to write down by what I multiply the whole thing. I'm going to multiply it by n plus 5. And if I calculate numbers over here, it's going to be n plus 6, right? So I'm multiplying the whole statement but by the product n plus 5, n plus 6. What is going to happen to this part, the left part? N plus 5 is going to cancel, and I'm going to get 3, n plus 6 over here. N plus 5 is going to cancel with this one. Here, I'm going to have n plus 6 cancel because it's n plus 1 plus 5, it's n plus 6, and I'm just going to get n plus 5. Well, what I can do here, I can divide by 3, right? And that's going to give me n plus 6, n plus 5, and maybe I can subtract n of both sides, right? Minus n here, minus n here, and I'm going to get 6 greater than 5. This is already obvious that it's true, so I'm going to write down true, but it's supposed to be really true, like really obvious. So this is true, means that the sequence is decreasing. I'm going to state decreasing. And that's very good. Now, sometimes direct inequality is not going to be easy to prove. Well, in this case, it's even like you can see it without inequality. This is example of how we do it with more complicated stuff. Of course, let's learn how to do it on a simpler stuff. Way number 2. Remember that we always can make up a function from a sequence. F n. So write down the sequence as a function in this like natural points, and we can write down that it's function 3 over n plus 5. And if you write it down as f of x, turn n into x, we are going to have 3 over x plus 5, right? Well, what is good? If the sequence is decreasing, the function is going to be decreasing too. If the function is decreasing, the sequence is going to be decreasing too. Erase a little bit this tree. So I'm going to show that the function is decreasing. How function is easier to show that it's decreasing? Remember that when function is decreasing, something important about this function is true, especially something important about derivative, right? If the function is decreasing, the derivative, just we know from calculus 5a that derivative is going to be less than 0, right? If the function goes down, then the slope of the tangent line is going to be negative. Let's calculate the derivative. Is it going to be true? So, well, let's see what is actually derivative of this function. So we have like I would not say that's a quotient. I would write it down like 3x plus 5 to the power of negative 1. That's gonna be easier to differentiate. So 3 is going to be a constant, and we are going to have x plus 5 minus 1 multiplied by negative 1 because that was initial power. Or if you write it down as a familiar fraction, it's going to be 3 over x plus 5 squared. Well, are we sure that this number is less than 0? Yeah, because this number is a square, is greater than 0. 3 is greater than 0. Sorry, 3 disappeared. And extra minus is going to ensure that it's less than 0. And why I'm writing down 1? No reason, absolutely. Looks like my hands are working by themselves. Less than 0. So the function is decreasing, then the sequence is decreasing too. Well, when do we use them? Of course, if something is very obvious, you don't need to use them. But sometimes it's not that obvious and you can use a derivative to show that something is decreasing or something is increasing as well. Again, just kind of remember about this. So why do we need all this? Well, I'm going to introduce with you more definitions and let me make it a little bit smaller, scroll it up. And next definition, or maybe a little bit bigger. Next definition, a sequence AN is bounded above if there is a number. Sorry. Not supposed to be here. There is a number M. Sorry, guys. M such that A and all terms of the sequence. I keep pressing something on my screen and all terms of my sequence are less or equal than this number for all n greater or equal than 1. Like for all terms are less than certain number. Well, I'm just going to give example of a sequence which is going to be bounded above. Let's consider a sequence 1 over 2, 1 over 3, 1 over 4, 1 over 5. What can be n? The big M, number which is greater than all of them. Well, we see that the numbers are decreasing and even like 1 over 2 can work as this number. For example, M can be equal to 1 over 2 and 1 over 2 is going to be greater than all terms. And including the first term because we have equal sign, right? So this 1 over 2 is greater or equal than all terms of this sequence. Can I use M equals like 100? Is it still going to be greater than all terms? Yes. So M is actually not going to be a unique number. You can make up like any number which is greater than all terms of your sequence. Okay? So, well, now sequence, second part of the definition. Let me change my color. Second part of the definition. Sequence AN is bounded below if there is a number. Well, maybe, oh, sorry. There is a number little m such that little m is less or equal than all terms of a sequence for all n greater or equal than 1. So kind of, sorry, it's supposed to be here. No, it's supposed to be here. So you see that the sequence can be bounded below and bounded above. Means that you have a greatest number and the smallest number. Over here, guys, I want to use the same sequence to kind of consider the example of bounded. So what do you think? Which number is going to be greater than all terms of the sequence? Which number can be like my little m here? Well, for example, little m can be -1. Obviously that all my terms are positive and they are going to be greater or equal than -1. They're not going to be really equal, right? Because they're all positive. Can I use little m equals 0? Are the all terms greater than 0? Actually, yes, right? Because they are decreasing to 0, but they're never kind of turning into 0. Works too. Interestingly, that the very same sequence is bounded above and bounded below. Sequences like these are going to be called just bounded. Maybe like next part of my definition, if an is bounded below and above, it is called just bounded. Well, we are not saying just bounded because actually it's more bounded than just below and just above, right? So not all sequences are going to be bounded, and not all of them are going to be bounded on both sides. I'm going to give you example of sequence which is just bounded on one side. Let's consider next example. A sequence of 1, 2, 3, and so on. You see that this sequence obviously has a lower bound or bounded below. If you consider m equals 0, it's going to be greater or equal than all terms of this sequence, right? Greater than 1, greater than 2. Well, maybe I should not write down them like this, an, right? But there is no upper bound because numbers are growing infinitely. There is no upper bound. No big M. Upper bound. So this sequence is bounded only below. There are sequences which can be bounded only above and not below. And there are sequences which are not bounded at all. I'm going to give you an example of a sequence which is not bounded at all. And again, I don't want you to write down the formula because I want you to visually see like how it's kind of working. Imagine that the sequence is 2 and minus 2 squared, then 2 cubed, then minus 2 to the power of 4, then plus 2 to the power of 5, then minus 2 to the power of 6, and so on. So we kind of have geometric sequence and it's alternating sign. Plus, minus, plus, minus, plus, minus. So you see that this term is 2, but this term is minus 4, and this term is 8, and this term is minus 16. So kind of terms grow in both directions. So we have no little m because these negative terms will go down to infinity, and no big M because positive terms will go up to infinity. So it's not bounded at all. Not bounded. So sequence can be bounded above, bounded below, bounded, which means below and above, and not bounded. Not bounded. So no restrictions of this sequence on any directions. Well, maybe about bounded, I'll give you example how we kind of show that it's bounded. For example, this is not like visualizing the definition. This is just example to show like how we work. Show, let's call it example. Show that an equals sine of n over n is bounded above. Let's try. So to show that it's bounded above, we'll need to find a number which is greater than all terms of this sequence. We're going to look at this sequence and see that for sine of n, we know that it's less or equal than 1, just by nature of sine, right? It's always less or equal than 1 because sine cannot be greater than 1. So if I divide it by n on both sides, I'm going to get that all terms of this sine sequence are less than 1 over n. Yeah, they can have a different sign and they're not going to be like equal 1 over n. But for 1 over n, we already know that we can choose like 1 over n sequence looks like 1, 1/2, 1 over 2, 1 over 3. We know that we can choose any like number greater than 1, which is going to be greater. So you can say that all of them are less or equal, for example, than 2 or than 1. You see? So your m can be equal to, or m can be equal 1, or m can be equal 1000. Just any number greater than. See? So, well, just know this, right? Now, guys, last definition or last theorem actually of our section 11.1 is monotonic sequence theorem. I'm going to use a different color to just separate this theorem from all other theorems we learned so far. Monotonic. Monotonic sequence theorem. Very simple. Every bounded monotonic sequence is convergent. Convergent means that it has a limit. I'm going to put it in parentheses. Has a limit. If you kind of don't remember like what is convergent. So it's telling if your sequence is monotonic and bounded above and below, bounded means both of them, right? Then it's going to have a limit. Of course, guys, we learned already lots of laws which are going to help us to calculate limits of the sequences, but sometimes they are not going to work. And then we probably are going to use this theorem. And I'm going to show you an example of use of this theorem. We don't use this theorem just for fun. We use it like a last resort, because it's going to show us that sequence has a limit and sometimes going to help us to calculate this limit when we cannot do it by traditional ways. Okay, so I'm not going to prove the theorem. Actually, the book has a proof of the theorem. You can read it. It's not complicated, actually. It's just using the definition. Remember, epsilon n definition of the sequence. But I'm going to concentrate on an example of how we use the theorem. And this is going to be kind of long example. So if you will need about 10 minutes or 15 minutes to watch this constantly to see how this example works. Okay, so my example, I'm going to prove that this sequence has a limit. Sequence is built next way. The first term of sequence is a square root of 2. Every next term is going to be built by the formula 2 plus the previous term square root. Looks a little bit strange, but remember that we can kind of make a recursive sequence like Fibonacci sequence. You build the next term on the previous term or terms. I'm going to show you how terms of this sequence are going to look. So we visualize it a little bit. The first term is a square root of 2. The second term is going to be a square root of 2 plus the first term, which is a square root of 2. And the next one is going to be 2 plus square root of 2 plus square root of 2. And, well, this is going to continue forever. So we are going to have more and more square roots under the square root. And here is not very obvious how to calculate the limit. Just we even don't know if the limit exists because like each next term is built from the previous term. And we will try to use this monotonic sequence theorem. To use the theorem, we will need to prove two things. First, that the sequence is monotonic. Monotonic means either increasing or decreasing. Do you need to prove both? No, sequence cannot increase and decrease at the same time. This way, it's not going to be monotonic, right? And usually, guys, you look at the sequence and kind of estimate like what it's doing, increasing or decreasing. Well, it looks like the next term is going to be a little bit better than the previous one, right? If it has no square root of 2 over here, that's going to be equal. But extra square root is going to increase a little bit expression under the square root. So the sequence is going to be increasing. We are going to prove it. So number V will use the theorem. A, check if AN is monotonic. Prove that AN, sorry, my N doesn't look nice. AN is increasing. That's what we're going to show, right? Increasing means that next term of a sequence is going to be greater than the previous term of a sequence. How do we kind of show this? Well, we're just going to use our formula for a sequence and write down next term and write down the previous term. And I think it's going to be visible maybe that it's increasing. If it's not visible, we probably are going to use a kind of a different method. Well, let's see. So my next term, an plus 1, is going to look like a square root of 2 plus an, right? That's how it looks. And we are trying to prove that it's greater than term an. Well, let's see. If we square both sides, we know that terms are positive because they are all square roots. Let's square both sides. We are going to have 2 an here greater than an square, right? And well, just like squaring both sides. Now, what we'll need to do to show that give me a second, guys. Maybe okay, what I think we will need to do, not just use direct inequality, but use a method of math induction. I thought maybe direct inequality is going to work here, but actually, unless you know where the terms are sitting, direct inequality is not going to work here. So I'm going to use math induction, and you guys probably forgot how math induction is working. Maybe I'm just going to remind you by doing this inequality. So I wrote inequality, right? And on the left side, I placed expression for the term, right? I'm going to place expression for the term on the right side too. Okay, so term, let me write down. So you're not going to be confused. If the term is not an plus 1 but an, then expression, the formula is going to be 2 plus an minus 1, right? So it's like previous term plus 2 square root the next term. And that's what I'm going to do. I'm going to place the expression 2 plus an minus 1. So it's kind of, I'm using the same formula, just here I'm writing down the next term and the previous term because it's using also the previous term. Now I'm going to do squaring and I'm going to get expression an minus 1. And you probably ask me, oh, well, how that's like proving anything? Doesn't prove anything. I'm going to cancel 2's and I'm going to get an equality that an must be greater than a minus 1. You see, we started with this inequality, an plus 1 must be greater than n, and we got to this inequality, but we still need to prove it because we don't know if it's true or not, because we don't know if the sequence is increasing, right? But you understand that you can repeat this square root for these two elements too, and have like element n minus 1 on this side, element n minus 2 on this side. And if you repeat this inequality many times, eventually you are going to get over here what? A2 and over here A1. And for these two, we can just manually check if it works. Let's do it. Let's write down what is A2. Look at my expression over here. A2 is 2 plus square root of 2. And A1 is just square root of 2. So I square both sides again, and I'm going to get 2 plus square root of 2, and here greater than 2, right? And what I'm going to do, cancel this 2 and get a square root of 2 greater than 0, which is true, right? So what I'm going to say, well, if I want to prove this, I'm going to consider this, and then consider this, and kind of move up to here, starting with this, and that's a true statement. When your proof looks like this, like you are doing a chain reaction over here. In math, proofs like this are called math induction. And usually, this is a way to explain math induction. But the method of math induction is a little bit shorter itself because people understand that they check like first two and then they always can go to the very original inequality. If it works, you can always go back to this one, right? So I'm going to write down kind of how it looks like when you use math induction. So this is like how actually math induction is going to work. You keep writing down these inequalities using the formula, and eventually you get to the very first inequality, which is true just because you can manually check it and get, yeah, that's true because the square root of 2 is greater than 0. But how math induction is going to look if you kind of like write it down academically. So I'm going to put it next to the proof, math induction. Math induction. Math induction is going to do everything in opposite direction. First, it's going to check that inequality works. For example, we are proving inequality that an plus 1 is greater than an. First, check for, let's say, n equals 1, how it works. For n equals 1, does it work? Well, we are going to write down that this is 2 plus square root of 2, and this one is just square root of 2. We already proved that it's going to work, and that's true, right? Second is called step of induction. What is step of induction? Step of induction is assume it is true for n equals k. So assume that it's true for some n equals k. So k plus 1 is greater than k. Prove that it is true for n equals k plus 1. So kind of move to the next step. K plus 2 greater than ak plus 1. Usually what we do, we write down what we'll need to prove and use somewhere what we already have as like assumption. So we're going to write down a k plus 2 less than ak plus 1, and we are going to use a formula. The formula tells us, okay, 2 plus ak plus 1 here instead of this, and 2 plus ak instead of this one, and then we are going to square it. 2 plus ak plus 1, 2 plus ak, then cancel 2, and get ak plus 1 greater. Is it true? Well, we are going to look at our assumption. Remember, assume that it's true for a, yeah, we are going to write on true by assumption. When you get a statement true by assumption, you did the step of induction. How? Well, you know that if for previous pair it's true, it's going to be true for the next pair. It's kind of, we can make a step. Now, what is the very first previous pair? This one. So from this one, we go to the next pair, to the next pair, and to the next pair, and we kind of pull all terms of this sequence into this inequality. And this is like how math induction is working. Basically, it's the same, just less visual, maybe like more academic. So we did step of induction. After that, you can usually write down, so by math induction, the inequality is true. Math induction is a very powerful method, but don't overuse it. If you can prove it just as an equality, prove as an equality. Just this one was not kind of possible to prove by just using an equality. Okay, now guys, we are going to prove that it's bounded because we just checked that it's monotonic. We know that it's monotonically increasing. So kind of we can use the theorem, but we still need, like we do prove that it's monotonic. Now we'll need to prove whether it's bounded or not. Bounded means that it's supposed to have upper M and lower M. Well, if you look at the sequence, you're going to obviously see that all terms are greater than 0, just because a square root is greater than 0, right? I'm going to write down over here like a question about that, whether it's bounded or not. B, bounded. Little m, which is greater or equal than all terms, can be equal, for example, to 0. All terms are greater because they are square roots. We know that the square roots are always greater. Okay, how about big M? Well, what can be used as upper bound? Well, let's go back to the sequence and look. What can be upper bound number? Well, guys, it's kind of hard for you probably to see what can be upper bound number. I'm going to use big M. Big M equals 3. I think that terms are not going to go over 3. So I'm going to prove that M equals 3 is greater or equal than all terms of my sequence. Probably I'm going to use math induction again, just because terms are given recursively and it's going to be a little bit easier. Now, guys, I'm not going to do this like bunch of inequalities. I'm going to do a standard math induction method. So to write down math induction. So number 1, I'm going to check whether it works for n equals 1. N equals 1. I'm going to have 3, supposed to be greater or equal than the first term, it's square root of 2. Kind of obvious, but you can actually prove it more. Square both sides, it's 3 squared is what? 9. And this square is 2, well, kind of true, right? We see that it's true. 9 is greater than 2, right? Now, assume that n equals k, it works. Means that 3 is greater or equal than ak. So that's the statement we're trying to prove. Need to prove. Oh, okay. Need to prove. It is true for n equals k plus 1. Need to prove that 3 is going to be greater or equal than ak plus 1. Well, how are we going to do this? We are going to use a formula for the term. Remember how the formula looks. Let's go back. The formula looks like this. So I'm going to use it. I'm going to write down square root of 2 plus ak. And I'm going to square both sides, like I did for the first term. That's going to be 9 here, and that's going to be 2 plus ak here, right? And I'm going to subtract 2 from both sides and get 7 greater or equal than ak. Well, is it true? Let's go to assumption, because we can use assumption. Assumption is our tool to prove stuff. Well, if ak less than 3, of course, it's going to be less than 7, right? Assumption tells that ak is less or equal than 3. And of course, it's going to be less than 7 then. So true by assumption. Okay, so we proved that this big M is like 3. Can be probably a different number, but in our case, we proved that it's bounded because it has little m and big M. So by theorem now, our sequence AN is monotonically increasing and bounded. Mean that it has a limit convergent. Well, how it's helping us? Because, wow, the idea that it has a limit sounds very nice, but what this limit is equal to? Well, because we do know that it has a limit, we can use now the theorems we had for limits. Let's write down how to find that limit. I'm going to write down the term. A n plus 1 equals 2 plus a n, right? I do know that limit exists. Means that I can put limit on both sides. Here and here. And because limit exists, I can bring limit under the square root. We can do all these manipulations with limits only when we know that limit exists. So I'm going to get limit of a n plus 1 equals a square root. Here, sorry, it's supposed to be 2 plus limit. 2 plus limit of a n. And n goes to infinity, n goes to infinity, and n goes to infinity. I don't have any space here to put n goes to infinity. Now, guys, if limit of a sequence exists, and let's say equals to number L, it's going to be a same limit no matter which term you use. Because like if sequence goes to a certain number, well, you can start with term n plus 1, you can start with term n, it's going to be the same number. What are we going to have, guys? If limit exists, we are going to have L equals a square root of 2 plus L. Can we solve this equation? Now we do have equation about number L, which we don't know. Can we solve this equation? Let's try. Square both sides. L square equals 2 plus L, and L square minus L minus 2 equals 0. If I kind of solve it, what I'm going to have two solutions. L minus 2, I'm going to factor it actually. I usually don't factor. I don't like factoring. Actually, I like to use Viet's theorem, finding roots using the formula. But I'm going to factor here because it's very, very easy. Like minus 2 and minus 2 plus 1 is going to give me minus 1. So we have two roots. L1 equals 2 and L2 equals 1 minus 1, right? If this one is equal to 0 and this one is equal to 0. So obviously that limit of our sequence cannot be this one just because it's a negative number and terms are concentrating in positive area. So that's going to be my limit. I found actually the limit. We can say that limit of a n as n approaches infinity equals 2. So we were right that big M is 3 and actually big M can be taken even less, right? The limit is actually equals to 2. Well, of course, we don't use all these theorems, complicated ones, for fun, like math induction. If you can use a different method, just inequality, for example, to prove, use it. But in some cases, it's not going to work. Usually it's not working when you have a sequence given recursively with like square roots and other stuff. Okay, I think that's all about this first section, and that was kind of long, right? I'm going to put a review problems. I'm not going to write them down over here. I'm just going to put them on Canvas, okay? Just to have them somewhere separately where you can access them without watching the video, okay? And my suggestion, do the homework and as many problems as possible. And of course, we are going to do some review in class. In the book, they do have a different sequence to illustrate how this theorem of monotonic and bounded sequence is working. You can read their problem and you can kind of, make comparison between my and their and see how like what is general for both proofs and maybe get this general idea. Okay. Okay, that's it for today, and I'll see you all in my next video.